All right, let's dive in. Today, we're going to tackle a really fundamental challenge, one that connects your brain, AI, and even cybersecurity. It's all about how we build a model of reality, and maybe more importantly, how we defend that model when it starts to go wrong. It all kicks off with a simple question, one I'm sure you've thought about. Why is it that you can't tickle yourself? I mean, you can try, it just doesn't work. And the answer? Well, it isn't just some weird party trick. It's a clue to one of the most incredible things your brain is doing every single second. The secret is something called an efference copy. Now, that sounds technical, but the idea is actually pretty simple. Whenever your brain sends out a command to move, say to wiggle your fingers, it also sends a little carbon copy of that command over to your sensory systems. That copy is basically a heads up, telling your brain, hey, we're about to feel something, but don't worry, it's just us. It predicts the sensation and cancels it out, so it's not surprising. And if it's not surprising, it's not ticklish. And that little trick reveals the brain's real job. See, your brain isn't just passively reacting to the world, no way. It's a full-blown prediction engine. It's constantly running this incredibly detailed simulation of reality. And to keep that simulation from falling apart, it has one absolutely critical task: telling the difference between its own signals, the self, and signals coming in from the outside world, the other. Now, the efference copy is just one tool in the toolbox for this. Your brain also has the thalamus, which acts like a sensory switchboard, deciding what to pay attention to. And then there's a part of the brain responsible for reality monitoring, literally tagging information as either an internal thought or an external fact. It's a whole suite of systems designed to manage the simulation we call reality. Okay, so this is where it gets really interesting. This biological process, it has a stunning parallel in the world of computers. On one hand, you've got the brain, using predictive coding to learn from experience. On the other, you have a machine learning model learning from data to predict outcomes. The brain has to distinguish self from other, while the ML model has to distinguish the patterns it learned from its training data from brand new data it's never seen before. It's the same fundamental problem. And to really get this parallel, we just need two quick bits of lingo. In machine learning, a sample is just a single data point. Think of it as one patient in a huge medical study. A feature is just a characteristic of that sample, like the patient's age or their blood pressure. Samples and features, they're the basic building blocks we use to teach a machine how to spot patterns. So how does this actually work? Well, imagine we want to teach a computer to identify different types of iris flowers. First, we collect a ton of data, the features, right? Things like petal length and sepal width. Then, and this is key, we split that data. We use most of it to train the model, letting it find patterns. But we hold a little bit back. That's our test data, which we use at the end to see how good the model is at classifying flowers it's never, ever encountered before. But here is the absolute crux of it all. Both of these models, the one in your head and the one on a computer, can break. And not just break in random ways, they can fail in very similar ways by making the same fundamental mistake, confusing their own internal patterns with what's actually happening in the real world. In neuroscience, you can actually see this happen when the brain's predictive model gets a little overenthusiastic. For example, under the influence of certain psychedelics, the brain's pattern matching system goes into overdrive. It starts to overfit its own internal library of images, geometric shapes, fractals, onto what it's seeing. It projects patterns that aren't really there. Now get this. This slide shows the exact same failure, but in machine learning. Just look at that chart on the left. The model is following every single training data point perfectly. It's basically memorized the answers. It has a training score of 1.0, perfect, but its ability to predict on new data, a test score of just 0.35. Oof, it's totally useless for the real world. It has overfitted. It's the same problem. So what we have here is a tale of two failures. For the brain, when those self-tags don't work right, you can get hallucinations. For a machine, overfitting means it can't generalize to new situations. In both cases, the model has lost its grip, confusing the map it created with the actual territory. Which brings us to the really critical question. If these models are so fragile, what do we do about it? How do we protect them? How do we harden our digital reality? This right here is the core challenge of modern cybersecurity. Think about an operating system like Windows 11 right out of the box. It's designed to be easy to use, to work with everything. It's not designed for maximum security. A lot like our brains, it doesn't come pre-configured to be a fortress. By default, it leaves huge attack surfaces wide open. And you can see how different organizations have totally different philosophies for hardening it. Microsoft wants to keep things stable. The CIS benchmark is all about defense in depth, layering on protections. And then you have the NSA, whose guidance is geared towards stopping nation-state attacks, even if it breaks a few things. It's a whole spectrum of how strictly you want to define the rules for your digital world. A really foundational defense in modern computers is something called virtualization-based security, or VBS. And this is just fascinating. It uses the machine's own hardware to carve out a tiny, super secure, isolated bit of memory that's completely separate from the main operating system. It's like the OS is creating its own little Thalmic gate to protect its most important secrets. So one of the coolest things VBS enables is called memory integrity. Here's how it works in 4 simple steps. When some code wants to run in the core of the OS, the kernel can't just trust it. Instead, it has to ask the secure VBS area, hey, is this legit? That secure area checks the code's digital signature, and only if it checks out does it give the okay to make that memory executable. Now, why is that a big deal? Because that simple process enforces one incredibly powerful rule. A piece of memory can either be writable or it can be executable, but it can never be both at the same time. This single policy, write, XOR execute, shuts down an enormous class of attacks where malware tries to sneak in some bad code and then run it. Hardening a system is really all about adding more and more of these specific rules. We can set up policies that say things like, nope, Microsoft Office apps are not allowed to launch other programs, or absolutely not, you cannot steal credentials from this critical security process. We are explicitly teaching the model what is and is not legitimate behavior. So let's just take a step back and look at the big picture here. We've talked about neuroscience, machine learning, and cybersecurity, and it turns out they are all wrestling with the exact same universal problem. First, the grain. It evolved these incredibly sophisticated filters and predictive models to build a stable sense of reality, to know the difference between a thought it created and something happening in the world, self versus other. Then, our machines. We're now teaching them to do basically the same thing, to build their own models of reality from data, and to learn how to distinguish the true signal from all the random noise. And finally, on top of that digital reality, we have to build our security systems. Their job is to be the ultimate defenders of that model, enforcing strict rules to distinguish what's trusted from what's untrusted. And why does this matter so much right now? Well, this quote from a system hardening guide just nails it. Our computers, our endpoints, they aren't just tools we use anymore. They are the new perimeter. They are the front line where our digital model of reality meets a very chaotic and often hostile outside world. Which leaves us with one last massive question to think about. As our digital and our biological realities get more and more tangled up, the integrity of these models, both in our heads and in our machines, becomes everything. So who gets to write the rules?